Anyway, he's employed as a geologist and paleobiologist.
Yeah, that's right. Yeah.
At Victoria University in Wellington, where he teaches undergraduate and postgraduate students. He did his undergraduate degree at Otago University and a PhD at Cambridge University before working at GNS Science in Lower Hutt for 20 years. After teaching part-time at Victoria University for a few years, he became full-time in 2019. This better be right, you wrote it.
Yeah, it's more or less right.
His three main research interests are mind-boggling. They are...
I didn't write that.
The large-scale evolution of biodiversity on Earth, the mathematical description of evolution within species, and the development of New Zealand and its life during the Cretaceous period. Absolutely fascinating stuff. It's just over a year since he last spoke to us about life and biodiversity being determined by competition, known as the Red Queen hypothesis, which refers to Alice in Wonderland's Red Queen, who had to run faster and faster just to stay in the same place. Similarly, he said, species must continually evolve new adaptations in response to evolutionary changes in other organisms to avoid extinction. James makes regular visits to Golden Bay, perhaps because the illustrious Victoria University Geology House is a mere stone's throw from the even more illustrious Mussel Inn, a great place to wash down the day's find of rocks or fossils with a pint of ale. So here's James back again, this time to talk to us about what the famous paleontologist David Rauch quipped to a first approximation: all life on Earth is extinct. I'm sure he'll give us an entertaining talk and leave us better education, if not extinct.
Thank you, Liz. Thank you. Well, thank you. It's lovely to be here. I apologise. I did mean to pack a slightly nicer shirt when it was a rush when I came out packing this trip, and I clean forgot, so you've got me in my field clothes. It's lovely to be here again. It's really nice. I love being in Golden Bay, actually a bit more than that. I'll explain that quote in a few moments. But firstly, I just want to say I have a very deep attachment to Golden Bay. I was brought up in Nelson, went to Nelson College, and a lot of my early tramping was in this part of the world. And I was back here actually just two and a half weeks ago, going along the Downard Range just before that big rainfall. And it was as dry as a crisp. And I actually have a question. This has got nothing to do with my talk, but I have to ask a question. The bird life was incredible. It was fantastic. But these little riflemen in the forest was completely dry. What do those birds do for water? Before it was the streams were dry, the tarns were dry. I don't know the answer. Somebody here might know. I don't know. Anyway, so I have a very deep affection for this part of the world, and my favourite place in New Zealand to go tramping is in Kahurangi National Park. So I just. I'm down here with a bunch of 15 students. They're second year. Can everybody hear me okay? That's it. I'm down here with 15 undergraduate students and Charlotte, who's our cook and camp mum, and I'm feeling really full right now because I've had one of her fabulous dinners. We come down here, there's 3 groups coming down here this year, 3 groups of about 15 each. We have the extremely old house at Onakaka. It's our field station. And it's teaching in the field. Geology is really a field thing. There's lots of high-tech equipment you can use to do geology, and you can look at the Earth from space using satellites, etc., etc. But actually, fundamentally, geology is about looking at rocks. I mean, geologists say, the best geologist is the one who's seen the most rocks. And that's still true. And these students come out here, and it's fantastic. In the space of a week, you see these second-year classes just gel together. These suddenly become really tight. You see these fantastic friendships forming in the space of the week, and you see, and the students, they totally get into it, and you see the light bulbs going on every day, and suddenly they're solving problems. And one of the things I tell them is, I did my PhD in England, and the London banks used to come up to Cambridge University recruiting, And they only went to 3 departments in the university, and one of those was the geology department, because they'd learnt that geologists make fantastic bankers because they can work with incomplete information, they can work with completely contradictory, complex information at a range of scales. And the students hear us do this every day. We seamlessly jump from what you can see at a microscopic scale to thinking about continental size problems, and then we jump back again, and then we're talking about processes that happened yesterday, and then we're talking about processes that happened 100 million years ago, and that thinking across time scales and across geographic scales. That's why the banks think we make good bankers, but it's it's what the students learn in these field trips. So I just wanted to give you a bit of a heads up why we come down here every year, and it's a fantastic, as a teacher, it's really, really satisfying. And the students have a fantastic time. And we've just got to keep the house waterproof, which is a challenge on occasions. Yeah, we'll see how we go in the next 24 hours. Anyway, so that's one here. And there's you all know where that is, I presume. There's a group of the students on a sunnier day at Downard-Wilke Beach. Okay, let's get back to the title of this talk. Incidentally, I've got 2 hours to speak, haven't I? So David Wright was a very famous paleontologist. Unfortunately, he died a few years ago. But he said, to a first approximation, all life on Earth is extinct. And, oh, crikey. I mean, the fact that I'm standing here talking to you suggests that probably isn't the case. And the fact there's been a continuous, non-stop parent-child, ancestral linkage going right back to the first life that evolved on Earth, 3.5 billion years ago. But what he was saying is, in fact, over that history, 99.99% of species are now extinct. So to a first approximation, everything's extinct. We're just the current iteration of life that's been on the planet, but most things have been extinct, are now extinct. Extinction is a fundamental part of the whole evolution of life, the whole development of biodiversity on the planet. Basically, a bunch of new things are not going to evolve, and a bunch of new species are not going to evolve until some species have gone extinct. And there's this, and it gets back to the Red Queen that you mentioned, this idea of competition, and something has to go extinct so something else can evolve, and that's more or less the case. So extinction is a normal, healthy part of the whole evolutionary process. It's how life has continued to, and life has continued to become richer and richer and more, I hesitate to say more diverse. It is more diverse now than it's ever been. But yeah, it's a normal part of the process. So that explains that. And so we've got this, this is the only slide that I showed last year that I'm showing again just because I like it. But we've got this incredible richness of life, these most bizarre, diverse, incredible things. And that's, so, and these are here in part because other things have gone extinct. So in this talk, I'm just going to give a very quick introduction about the discovery of extinction, because actually it's quite interesting in itself. I'll give just 2 examples. I'll talk about the Cretaceous Paleogene mass extinction, and I'll talk about the Quaternary megafaunal extinction. I'll explain those, obviously. And then I'll just talk a bit about extinction now and in the future, and what we can learn. A few overarching considerations. One, it's an unfortunate reality that we can only really know about extinction after it's happened, when it's too late. We really only know something's going to go extinct. There's things alive now that should have gone extinct. The Tuatara, that was a hugely diverse group of organisms. There was hundreds of species all around the world about 150 million years ago. Over that 150 million years, there's been one has survived right through to the present day in little old New Zealand. It should have gone extinct with all the other ones, but it didn't. Conversely, so that's an example of something that you had thought it would have gone extinct and hasn't. The flip side of that is things like the passenger pigeon in North America. That there were flocks of passenger pigeon in the mid-1800s, flocks that would take 3 days to pass overhead, and yet they were driven to extinction in a matter of 20 or 30 years. So nobody in their right mind would have predicted a bird. It was the most abundant bird on the planet. Nobody would have thought you could possibly make that extinct just with a few guns, but they did. So my point is, extinction, there's a strong element of unpredictability in that. You can only know after it's too late, and that's not what we want. So my question is, what can we learn from the fossil record about the causes of big extinction events? What can we learn about selectivity of extinction? And by that I mean, are there particular groups of organisms are more vulnerable to extinction? Are there particular groups or particular regions of the Earth that are more resistant to extinction? It's useful to know that. How quickly do ecosystems recover from big extinctions? And what can we learn anything useful? What are the implications for us living on the planet today? Okay, the recognition of extinction is an interesting thing. Prior to about the when was it? It's about the late 1800s. People didn't know about extinction. People thought that life had been created perfect by the Creator, and then absolutely it was unthinkable that the Creator would allow one of his perfect groups of organisms to go extinct. So people actually didn't even acknowledge extinction was a real thing. But then people started finding the bones of mammoths and giant ground sloths and all these other things, and clearly they weren't alive in Europe at that time. And that people, for a while, people assumed, well, these must be still living in deepest, darkest South America or Africa or somewhere like that. We just haven't found them living. But slowly, as the world became more explored, it started to realize there truly were things that had been living now that weren't living. And this, Georges Cuvier was the first person to really recognize that extinction was a thing, that extinction could happen, had happened in the past. And that's Charles Darwin, and that's just a gratuitous picture of a dinosaur. And then following Charles Darwin's work, it was thought that extinction happened, but it happened gradually. It was one species will go extinct this year, and then in 1,000 years' time, another species will go extinct. And it was he thought, like evolution, extinction was this very continuous, gradual process. But then, so that was this gradualism idea. But then in 1950s, this German paleontologist, Otto Schindelwulf, he recognized that in fact there were times in the past when there'd been the sudden disappearance of many species. And he thought, well, so it seemed like it wasn't a gradual process, not all the time. And it was this guy, Norman Newell, a famous American paleontologist in 1963, who coined the term mass extinction. This idea that there were times when there'd been a whole load of extinction going on. And that really did spawn an industry of mass extinction. And in 1980, Walter Alvarez and his son Louis, was Walter the father? I forget which way around it goes. Anyway, it doesn't matter. He was an astrophysicist, and he detected at the end of this famous extinction when the dinosaurs disappeared, he detected iridium in the layers of rocks. And one of his 3 sites was in New Zealand, actually. I'll show a picture of that in a minute. He detected iridium. He said the only place the iridium can come from is from space. And so he was the first one to recognize that perhaps every so often there was a mass impact from an asteroid or a large meteorite or something, and that had caused a mass extinction. And then these 2 famous, Raup and Sepkoski, Raup you've already met, he came up with the idea that there were 5 of these major mass extinctions throughout Earth history. And then a little bit later they came up with the idea that actually mass extinctions, there's a 26 million year, every 26 million years approximately there's a mass extinction. And they said there's some periodicity and it must be caused by something to do with space. Perhaps the solar system passes through a region of space where there's more asteroids or something. And there's been hundreds, if not thousands of papers, scientific papers written about this. So that's just a little bit of background about the whole recognition of extinction. The first example I'm going to talk about is what's called the end Cretaceous mass extinction, or the Cretaceous-Paleogene boundary. Cretaceous is one period, the Paleogene period is the period that came immediately afterwards. And it's famous because it's probably the 2nd biggest mass extinction in history, and it's famous because these guys went extinct. Just a little aside here. The dinosaurs did not become extinct. Technically, birds are a subgroup of dinosaurs. Birds are dinosaurs. They're just a little subgroup, one little subgroup that managed to survive, but the wider group that enclosed them which is now called the non-avian dinosaurs, the non-bird dinosaurs. So that is a non-avian dinosaur, and the sparrow flying outside is an avian dinosaur. Anyway, most these big non-avian dinosaurs became extinct. And following the work of the Alvarez father-son team, they came up with this impact hypothesis, and apart from anything else, it's generated a huge amount of really spectacular art. And in a nutshell, they figured out that about a 10-kilometer size asteroid hit the planet. Astronomers have now even worked out where that asteroid came from. It hit 160 million years ago. There was a collision in the asteroid belt. That collision knocked something out of orbit. 66 million years ago, so almost 100 million years later, that hit Earth. I say a 10-kilometer thing, it would sort of fit in Wellington Harbour like an egg in an egg cup. It's about that sort of size. It hit the planet. When it hit the planet, it released more energy than about 100,000 times the entire global nuclear arsenal at the height of the Cold War. So you put all the global nuclear arsenal in one place and you multiply it by 100,000 times and you light the fuse, and that was the sort of energy it released. And it generated lots of art. There's lots and lots and lots of evidence for this. I will show a few bits of that later on. For a long time, people said, well, where's the crater? And it took a long time, and they couldn't find the crater. But then they did. They were searching for oil in the Gulf of Mexico, and the Yucatan Peninsula, Mexico, it's a buried crater. It's completely buried by younger layers of strata. But the geophysicists looking for oil, they have these ways of looking into the crust, and they started doing all this imaging and trying to find the oil deposits. And what they imaged was this 200-kilometer diameter crater that, as I say, it's completely buried. You can't see that at the seafloor. It's deep below the seafloor, and it's situated partly on land and partly offshore in the Yucatan Peninsula. And then they've drilled into that. They've precisely dated that crater. It dates to the instant the dinosaurs became extinct. And we have, as I said, the Alvarez team. One of the sites they looked at was in New Zealand. Woodside Creek in Marlborough. It's a now famous layer. You can see it's a mass extinction because that's a mass extinction of students. No students were harmed in the taking that photo. That layer in there, there's a clay layer. This is a close-up. Those are 10-centimeter divisions. There's a clay layer there that records. In the strata beneath that is full of Cretaceous microscopic fossils. The strata above it become full of younger microscopic fossils, completely different species. In that layer, there are tiny little sand-sized glass beads. Those are the little bits of glass from when the asteroid hit. It vaporized a whole load of the crust. It's formed this blanket of little, initially molten, but they quickly cooled glass beads. Well, that's not a good sign. Any ideas why that happened? The computers. Oh.
If you just touch the computer board,
You reckon that's it?
up again.
Don't think so.
No,
It's the computers. The computer's awake.
Right, technical team swings into action.
I'll leave that to you.
Yeah. While that's happening. Anyway, so it vaporized a whole load of the rock. Hopefully, I'll show you a video in a minute. And all this molten material then formed a blanket around the planet, and then fell back to Earth. And at the time, New Zealand was about as far away from Mexico as it could get on the planet. So that layer contains these glass beads. It contains iridium, that element that's really only found in space debris that came to Earth. So the iridium, the asteroid hit the Earth and spread iridium around the planet. It contains soot from the wildfires that were generated. It contains lots and lots of evidence of the asteroid impact. Yeah, that's a bit weird. Does it
Sit
sound?
on.
Okay,
I'll put it on.
Yeah,
it's back on, but we're going to have to wait.
it's okay. I can
until
keep
last
talking.
time.
So we have this sites, and we've now got a number of sites in New Zealand that have this layer of clay that's got all those telltale signs of the asteroid impact. That's very strange, isn't it?
Yeah.
Technology.
It could have been a glitch in the launch.
Oh, okay. Oh, well, that could be. Yeah, it's coming on. I just probably need to start the show again.
Good question.
There we go. So there you go. We're back to our mass extinction. It was concern over that. It was a health and safety blackout. And so that's the layer. That's the instant we record in this layer strata in Marlborough, the instant that asteroid hit. Now, so there's just another gratuitous bit of art. But you watch this video. This is amazing. So people are now modelling the effects of that asteroid hitting. So this video is going to cover the first 10 minutes after the impact. Okay, and it's only showing half. The crater is forming here. There's the asteroid incoming, 10 kilometre diameter or a bit more in this, and this is going out 250 kilometres. And I'll just play it once, and then we can perhaps play it again. Hopefully, I'll play it. So you look at that, and we'll talk about it in a second. And you see the water goes a kilometre up into the air, and then there's this about a kilometre or 2 kilometre high tsunami that's spread out around the planet. So this is in seconds. So obviously it's not running in real time. It's running slightly faster than real time. And there's this 1 to 2 kilometre high tsunami spreading out. So I don't know if you noticed, but when that thing first hit, it excavates a hole about 20 kilometres deep, and then almost immediately the sort of the fluidized rock then bounces back up to a height of about 10 or 20 kilometres and then settles down. I'll just run it once more and you can watch those things, and then you get the massive splash, the water driven kilometres into the atmosphere, and then it falls back down and sends out this wave. I'll just show that once more because look at that. I mean, it's hard to imagine. And you see there's the fluidized rock is bounced way up into the atmosphere, and then off it goes. So people are doing all sorts of fancy stuff, and there's lots of interest now. You know, barely a week goes by that we don't see some little news item that NASA are watching yet another asteroid that's going to pass by Earth very close and so on. Sooner or later, we're going to have to worry about that. Oh, that's not what I meant to do. I didn't mean to show it a third time. Now, next. So that's what happened in the first 10 minutes after the impact. What happened in the following day? There's a fantastic deposit in the US. This is in Hell Creek up here. And this was, North America at the time had a deep seaway going into North America. And Hell Creek was right up here. And the tsunami came up, was channeled up there. And what they found at this particular, it was a stream at the time. This is what it looked like at the time. There was a stream. And they found all these amazing fish fossils. They're things that are like a pike, they're about 50 centimetres long. They found hundreds of them on the layer, all lined up. And you know, and all their gills are completely choked with those little glass beads. So what the interpretation of this is that they are all lined up because the tsunami came rushing up the stream. The tsunami was full of debris, glass beads from the impact, and that choked the gills. And these things were all lined up because the current was the tsunami was rushing up the river, and they got their gills choked with glass beads, and then they got buried by all the debris dumped by the tsunami, and then they've been preserved. A fantastic deposit. So this is something that happened. I would have been some hours after, by the time the tsunami travelled up there. So there's amazing records of this. Something that has only just been recognised in New Zealand. This is at Tora in the Wairarapa coast. And again, that's the hammer, 60 centimetres long, just for scale. Geologists always put their hammers in their photos. And this layer here is the end of the Cretaceous. There's Cretaceous fossils in these rocks, and there's no Cretaceous. These are younger fossils up here. And I'll just put you don't need that. And then immediately above it, there's this layer, and you can hopefully see it's full of great big chunks of rock, all mixed up, smashed up, that have been torn off, these layers actually in places, and deposited as a chaotic layer of just debris dumped on top of that layer. And the current interpretation, there's people doing modelling of this, it seems from the computer models, because of the geography of the continents on the planet, it seems one of the effects would have been that the tsunami would have been particularly intense around New Zealand at the time. It would have been focused down the Pacific because of submarine topography, and focused on New Zealand. And the current thought is that these deposits may be the New Zealand expression of that huge tsunami. Still working on that, but it's just interesting to think that might be in New Zealand. So I've talked about the impact, and we know the impact happened. We know it had a catastrophic effect, but we also know that there was astronomical volcanism going on at the same time, forming what are now known as the Deccan traps in India. A large part of central India is up to kilometers deep in these frozen volcanic lava flows, up to, I think they're up to 3 kilometers thick in places, that were coming out at precisely the same time. I say it was something like somewhere between 1 and 4 million cubic kilometers of lava was erupted over a geologically short period of time. In fact, it seems like, so this photo is just, these are lava layers, successive lava layers that just flowed out of these volcanoes and covered a vast area of what is now India. And they think that the lava was erupting at a rate of perhaps 50,000 cubic kilometers per century. I mean, think of what a cubic kilometer of lava, I mean, that's a rate that humans have never witnessed, are very unlikely to witness. So we know that there was vast amounts of lava, and that was releasing carbon dioxide, it was putting dust and aerosols in the atmosphere that would have blocked the sun out. It would have had all the effects that you would expect massive volcanism to have. Scientists do tend to get quite polarized, and the scientists running around saying the extinction was entirely due to the volcano, and other scientists saying, no, that's absolute rubbish, it was due to the asteroid. And clearly both things were having an impact. And so I've sort of thought a lot about this, and I suspect, I mean, we know both things were happening. It's possible the asteroid, although it would have been catastrophic, it's possible it only had the impact, the massive destructive impact it did, because the whole system was already under stress. The volcanism, which had started just beforehand, had already really stressed ecosystems on the planet. And then, in a stroke of incredible bad luck, an asteroid came in and just, oh no. So the system was overwhelmed. And people are thinking about this, and they look, and this is slightly, I don't like this diagram. So this goes back to 260 million years ago, and there's the present day. So 260 million years, and the black bars are the timings of a whole bunch of significant extinction events. And the other black bars below, this is when there were these massive volcanic eruptions. They're called flood basalts because they flood vast areas of the globe. And this is when we have known impacts. And you can see most of the extinctions seem to line up with times of massive volcanism, although some of them line up with extinctions. And of course the one at the end of the Cretaceous, which is that one, lines up with both. So yeah, it was a bad day. That extinction at the end of the Cretaceous was not the biggest in global history. The worst one was at the end of the Permian, which is, where's the end of the Permian? Which is the one down here. So at the end of the Cretaceous, about perhaps 75% of species on the planet went extinct. At the end of the Permian, about 96% of the species went extinct. And that seems to have been entirely due to the huge volcanic eruptions. In that case, at that time, in what is now Siberia, and that's the Permian Siberian traps. Again, astronomically huge set of volcanic deposits. Okay. So the question is, how long did it take? Well, anyway, you've had this catastrophe in the end of Cretaceous, you had the volcanism, you had the impact. How long did it take the ecosystems to recover from that sort of hit? And this is looking at terrestrial fossils of the small mammal things that did survive through, the rats, the rodents, they survived. And looking at their body sizes, how long did it take to get up to a reasonable body size? And this is time after the impact, so 0, 200,000, 400,000, up to 1 million years. And you can track exactly how body sizes increase. And the body size is a good sort of measure of how complex and how complete the ecosystem was, how good the food chain was. And you can see after 1 million years, you're getting back up to 48 kilo animals. You're getting up to an ecosystem that's supporting reasonably large animals. You can also look at the plants. Initially there was just fungi actually, but then ferns appeared, and then you have what they call palm wool, that palms flourished, and you had legumes, and eventually again you got up to more complex plant systems, plant ecosystems. So that took about 1 million years. In fact, if you look at the so there's a complex cascades of environmental and ecological impacts. This thing, when the asteroid hits, it shuts down photosynthesis, so the herbivores have nothing to eat. Then the carnivores have nothing to eat. It puts a whole lot of acid into the ocean that has all sorts of effects on larvae of all sorts of species. It dissolves the shells of things. You get fallout of all sorts of toxic chemicals. You get initial massive cooling because of the dust in the atmosphere, and then you get massive warming because of the greenhouse effect of the carbon dioxide, etc., etc. You have this really complex set of systems that kick off, and it takes a long time for that to sort of re-establish some sort of normality. And what we can see is that the ecosystem recovery goes in many complex processes. Initially, you get what we call disaster species come in, like the ferns. Things, just as if you go out and burn a section of native forest, one of the first things that comes back is the ferns. They colonize. They're a sort of disaster species. And you see that in the marine realm as well. And you see these disaster species come back, but it's a really sort of out of kilter ecosystem, and then slowly other things appear, and you start to build up the complex food webs and so on that you need for a healthy ecosystem. In the oceans and on land, you can see that there's some sort of recovery in about 10,000 years. It's the beginnings of some sort of recovery, but it's still a very unhealthy ecosystem. And one way you can look at this, you can look at the carbon cycle that was in the ocean. The carbon cycle is an essential part of how all the global ecosystems work. You need to cycle carbon through the system, and you can measure that in the ocean, in the fossil record of the oceans. And it took about I can't remember what I said there, a few tens of thousands of years, but the carbon cycle to get full recovery took much longer. And in fact, it seems like it probably took about 5 million years for the ocean ecosystems to fully recover. So yeah, you start to get life back after a few thousand years, but actually to get the Earth back to a reasonable biodiversity, back to a reasonably healthy ecosystem, it took about 5 million years. So we're looking, these are big numbers. These are big numbers. Okay, that's the end. I don't know how I'm going for time. I don't know. I really don't know. It's okay. The second example I want to go. So that's an extinction that happened 66 million years ago. Okay, I'm going to now look at one that happened a few tens of thousands of years ago, and that's what we call the Quaternary megafaunal extinction. It includes our dear our own moas, but a lot of other things. It happened globally, and basically between 45,000 and 10,000 years ago, 65% of the large land animals, which we call the megafauna, so things over 45 kilograms in weight, 65% of them globally went extinct, including the moa. And this is now known as the Quaternary megafaunal extinction. This is only things on land I'm talking about. And it includes the mammoths and the woolly rhinoceros and the giant ground sloths and so on. I'll show some photos of some of them, not photos, some images of some of them in a minute. I wasn't actually around at that point. Sorry, I hit the wrong button. So this has been hugely controversial. There's been a whole bunch of scientific papers written that said it was climate. This extinction was caused by climate, and they talked about climate changing the water cycle, and warming events or cooling events or whatever. This is just an image from Australia. And the megafauna there included the giant kangaroo, the diprotodon, which is essentially a wombat on steroids. I mean, these things were huge. They weighed about a ton. The giant Komodo dragon, a whole range of things. Giant, all these over 45 kilos. And so there's been lots and lots of scientific papers that said it was climate that caused that. So climate what done it. But there's been a whole load of scientific papers that say it's humans what done it. So, it's linked to humans, not climate, humans rather than climate did it. And there's an image of some mastodons from North America and then the European woolly rhinoceros. And so there's been a whole load of scientific papers that said actually it was humans that caused the megafaunal extinction. So humans what done it. And recently, in the last few years, there's even people said there was actually there was an extraterrestrial impact. Well, not an impact. They said there was an airburst, so an asteroid hit the atmosphere very obliquely, and it didn't actually create a crater, it didn't actually impact the planet, but it caused an airburst, much like the thing at Tunguska that hit in the early 1900s, you may have heard about. It was witnessed by people on a train. There was an asteroid, it must have been much smaller, that came through the atmosphere and got so hot it actually effectively vaporized before it actually hit the Earth, but caused this huge explosion. And I should get the figures, but over a very large area of Siberia, all the trees were flattened, all pointing away from the center of the explosion, and it was witnessed by people on a train. And so it's thought that there's people who've claimed that this happened to cause the megafaunal extinction. And so there we go, you can know what's coming next. An asteroid, what done it? So there's been, and again, the literature and the debate and the argument, you go to scientific meetings, the arguments are spectacular and really become quite unpleasant. I don't have the answer. I have opinions on the subject, but my point is, even in the case of a very recent and well-studied extinction event, it's something that happened only a few tens of thousands of years ago, there are still many controversies. We still haven't resolved that. But it does seem like the end of the dinosaurs, the non-avian dinosaurs, where you had eruption and impact, it seems like multiple stresses, having multiple things happening at once actually is a big problem. So if you do have some climate changes going on, perhaps there was an asteroid, I don't know, and you had then humans doing a little bit of overhunting, you only need to increase the death rate of the youngsters, the juvenile population coming through to drive extinction. So a combination of things, it seems like, may have caused the megafaunal extinction. Personally, my opinion is that the humans were the ultimate primary driver of that. I think these were animals, organisms have gone through many glacial, interglacial cycles in the last too many years. They've done just fine. And I think, yeah, the climate change was going on, there were other things happening, but I think that the new kid on the block, us, was the final thing that, and it may have been that some of those populations were always quite fragile. The Moa in New Zealand clearly, didn't have a lot of capacity for withstanding extra death rates, but anyway. Even so, the debate continues, and I think it'll be going for some time. So I just want to now just briefly think about what can we, by looking at the fossil record, and that's just two examples, there's lots and lots of different areas, work going on in this area, but what can we possibly learn that might be relevant to us now? And again, I'm not going to go into a great deal. Well, this is the only graph I'm going to show, I think. But this study that appeared in 2016, and they looked just for the last 70 million years. So that's the end Cretaceous. That's where the dinosaurs became extinct. And they looked at mollusks and marine vertebrates, just because that's what they had good data for. But assuming that those were a good sort of proxy for what the general environment. And they looked at so this is the rate of extinction, how much extinction was. So it was high at the end of the Cretaceous when there was volcanic eruptions and asteroids. And then they looked at the extinction rate since then, and then they tried to look at what might be happening into the future, both for the mollusks and the fish, the vertebrates, both for a pessimistic scenario, so and the pessimistic scenario is the filled symbols, and the optimistic scenario is for an optimistic. Did I say that around the right way? Or the optimistic scenario, and they had a range of estimates from low estimates to high estimates. And the point is, what they said under the pessimistic scenario, we're running the risk of having an extinction rate that equals the end Cretaceous, and obviously that's of concern to us. There have been a couple of other really nifty studies. This one was actually done by a former PhD student of mine, and came up with a mathematical way of using past extinction, of a whole huge database of past extinction, to try and look at what might happen under future climate change scenarios, and quantifying that around parts of the globe. And in parts of the globe, so this scale, I never knew why she did this, but it goes from low extinction to high extinction on the bottom. That should be the other way around in my mind, but anyway, it doesn't matter. But many parts of the globe seem to be relative. This is looking at marine bivalves, again, marine clams, as a proxy for the wider health of the marine ecosystem, which is a reasonable thing to do. Clams are a good indicator of sort of species. And many parts of the globe seem to be relatively resistant, have good resistance based on using the fossil record to calibrate future risk. But I draw your attention, you know, New Zealand actually is high risk. We've got a high risk here. And there's another study. So that's for marine things. Very similarly, there's another study done for on the land, terrestrial things living on the land, and used a completely different method, but again, trying to use the fossil record to look at future extinction risk. And New Zealand certainly isn't the worst, South America is, but New Zealand's getting up there, has a reasonably high extinction risk. So New Zealand is vulnerable, and we know that anyway, and we treasure our species, but I'll talk a bit more about that in a minute, but not much. I don't want to. If I just want to wrap this up, I'd say extinction is normal. It's a normal part of evolution. You can't have evolution without having extinction. That's normal. But mass extinction is not normal. You have to have exceptional circumstances. You have to have the planetary scale volcanism or an asteroid impact or some combination thereof to have a mass extinction. That is not normal. There's some evidence. People talk about us being in the 6th mass extinction. So I talked about, you know, the recognition of 5 major mass extinctions in the past, and people now talk about us being in the 6th mass extinction. I don't think that's inevitable at all. But it's something we have to think about. Perhaps we're on the way to a mass extinction now. We can use the fossil record to help us understand future extinction risk. For example, we can look at the fossil record, and I didn't really talk about this, but we can look at which particular groups of organisms are vulnerable. You know, if you're looking in the marine environment, is it the things swimming around in the water are more vulnerable, or the things that live on the bottom? Is it the things that burrow into the seafloor? Is it the things in warmer water or the things in cooler water? Is it the predators or is it the grazers? You can look at all these things, and we're doing this work. In fact, I've got a student working on this stuff right now. You can look at that and you can come up with ideas, well, actually this particular ecological group is more vulnerable than the others. And then you can see where that ecological groups, and it can help you tailor where you might put your marine reserves or your reserves on land or whatever. It can help you tailor your whole conservation strategy, because you know, well, actually we can see that this particular group of organisms are going to be more vulnerable than the others. But in New Zealand, we have this sort of closed ecosystem. We're sitting in isolation in the middle of the Southern Ocean. You know, our animals and plants on land can't go anywhere else, and likewise, the things around our shores really can't migrate. You know, things that are used to living in the coastal waters can't just jump across to Australia. They don't do that. So we can use the fossil record to help understand how extinction works, and that gets back to that whole thing I said, you really only understand extinction after it's happened, after it's too late. And we don't want to wait for that. So we can use the fossil record, which is countless examples, natural experiments of extinction. It's all happened before. We can use that to help inform our policy now. But it does seem like natural ecosystems are particularly vulnerable when they're exposed to, when there's more than one thing happening at once. Climate change, predation, habitat loss, asteroid impact, volcanism, whatever it is. If there's more than one thing happening once, then your system, it seems that the ecosystem's actually relatively robust to one thing happening at a time. It's when you get that unfortunate coincidence of stuff happening that you have a problem. Environmental and ecosystem recovery from mass extinction might take hundreds of thousands of years or many millions of years. And on a geological timescale, that's not very long, but on a human timescale, obviously, it's out of the picture. I mean, you know, it's way beyond anything we can deal with. New Zealand has this is a worry. New Zealand has a relatively high extinction risk, but New Zealand has shown itself to be remarkably innovative in slowing or stopping extinction. I think of the clearing of predators from Campbell Island. We were the first place in the world to attempt anything like that, and we did it spectacularly successfully. I think of Zealandia, you know, the predator-free zone in Wellington. Wellington is, there was an article in the international media a short while ago saying Wellington is the only capital city on the planet where biodiversity is increasing. But biodiversity around Wellington is fantastic now. When I go for a run at lunchtime, I see saddlebacks. You know, it's fantastic. There's kaka. I have flocks of kaka passing the window of my office, you know, a dozen at a time, squawking away. It's fantastic. So New Zealand, and this whole idea of making all of Wellington predator-free, so they started on the Miramar Peninsula, and they're slowly moving the front across Wellington of traps, and the whole community's getting behind it. They've reintroduced kiwi in the Makara Hills, and they're breeding. You know, that's fantastic. You know, I was up on the Downard Range in the Kahurangi National Park a week ago, and the bird life. DOC have done these huge predator control operations, and the bird life was spectacular. I honestly haven't seen such bird life for many years of tramping. So we're good at it. So we have a high extinction risk, but we're also very good at doing stuff about it. And we can control this. So look, I feel really optimistic because I think we are good at doing stuff about it. And this recent tramp in Kahurangi really filled me with joy because of. Yeah. So on that note, I'm going to stop talking, and I'm happy to answer any questions. Yes, hot off straight off the blocks.
You mentioned the stability that complex ecosystems have, and I was wondering, when an extinction event happens, is there a synergistic effect on the extinction rate as the ecosystems become less complex?
Yeah, absolutely. And so there's been some really good work done recently showing the more species an ecosystem have, the more resistant it is to perturbation. Actually having diverse ecosystems actually makes them, and you can show this in all sorts of different ways. So if you've got lots of, and it's sort of one of the explanations, there's probably more than this, but it's this whole idea of redundancy. So if you've only got one herbivore in the system and it goes extinct, then everything else is wrecked. If you've got 20 herbivores, one can go extinct and the others can fill that role. It's having that multiple species doing each ecological niche makes your system much more resistant to perturbation. So I'm not sure if that answers your question, but yeah, so I mean, it's the classic thing. You know, if you've got a pine monoculture, it's a much less diverse and much less healthy and much less resilient ecosystem than a chunk of lowland podocarp forest with thousands of species. I read a fascinating thing the other day. You know those lovely little purple, some of you would have seen those little purple fungi you get in the native forest. It's beautiful. They recently analysed one of the forest moa. They found a gizzard, and they analysed that, and it was full of the spores of this fungi. And they've realised that the fungi is like a truffle-like thing. It was selectively eaten by the moa, and that fungi is a very important symbiont of many of the trees. And they think the moa would eat the fungi, spread the spores far and wide, and would help keep the trees inoculated, keep the forest healthy. An important part. And it just shows those complex connections. We've lost the moa, there's nothing grazing these fungi, there's nothing spreading them around. And hopefully, you know, I mean, that's not a critical thing, hopefully, but it just shows how these connections are so unpredictably complicated in a healthy ecosystem. I don't know if there's anything else that eats those purple fungi. I love them. I think they're fantastic things. Yes?
It seems that one of the problems that we have is that we now work with nations, and nations can feel like they're doing a good job or a poor job, but nations are very small regions of the globe. And when you look at the maps from the students who have done with the risk of plants, you're talking huge areas that are at greater risk. So as far as the planet goes for avoiding extinction, you need massive response in huge regions of the earth, not just individual countries doing their bit.
And you're absolutely right. And the only answer I have to that is we can't control that. We can control what we do here. Yes, you are right. And there are a lot of countries out there that care deeply. There's some, I don't need to mention them, that clearly don't at much. But I feel optimistic. I think and there's a lot of cases around the world, new whale species newly re-inhabiting parts of the ocean where they've been missing for a long time. You know, they've reintroduced beavers to Britain, and there's a lovely article I read recently. They've just started introducing beavers to England, and the farmers who've done this have said it's transformed their land, because it's suddenly created this ecological. Suddenly there was a pond where there wasn't a pond, and then they have healthy grass growth through other areas where they didn't before in the dry conditions. I mean, having all these amazing flow-on effects and happening really quickly. You know, within a week the beavers have built a dam, and they've suddenly created a bit of habitat. So you're right. There's also a lot of very good things happening, but you are right. Up to a point, we have to be optimistic. Yeah.
James, regarding the KT boundary 66 million years ago, I remember all the discussion in the scientific literature about whether it was an asteroid or whether it was the Deccan Traps. And we had the privilege of seeing an astronaut giving a lecture to us. We were about this far away from him.
Yeah.
And he said that he had an hour to do his own experiments every Saturday. And what he did was he made this ball of water hanging there in space, and then he fired a little shot of water, a little drop of water at one side, bang, and the drop of water came out the other side. And I said, that's a really good analogy for what would have likely happened 66 million years ago. The asteroid hitting the Yucatan Peninsula would have sent the volcano out the other end in India.
Yeah, it was, but the volcano had started before the asteroid hit, actually, so it was already going. Not long before, but it had definitely started before. Yeah, good idea, but New Zealand was right. New Zealand was exactly opposite at that time, and yeah, I don't think we've got any evidence of anything flying off. But yeah.
I recently heard it was a one-off news announcement that somewhere in Europe, and I think it might have been Czechoslovakia, these councillors had put aside quite an extensive piece of land because they wanted to renovate it and make it more viable for the wildlife. Anyway, they took about 6 years to come to their decision, and finally they gathered everyone together and decided to go out and see it. And the beavers had got in there, and they'd done exactly what they had been planning to do. It was going to cost millions and millions of dollars, but they've done double.
I saw the same article.
They've done double.
For nothing.
Double for nothing.
Yeah, no, I read the same article. That's fantastic. And beavers, and there's things we call ecosystem engineers. They're particular species that have an outsized effect on the ecosystem. They do something big that then creates habitat for lots of other species. Yeah, it was a fantastic article. Yeah. Yeah.
You mentioned that one theory was that there's about 26 million year periodicity. I was wondering if that's related at all to the galactic motion.
Well, that's how it was explained, that every 26 million years the solar system moved through a particular part of the galaxy where it was subjected to more impact. That 26 million year story now, I think, is not particularly strongly believed, although it's still there. People are still, in fact, somebody's now said, well, actually, it's 62 million years. There's still a debate going on. It's a long way off being proven. I think it may well turn out to be right, but yeah, there's still a debate. But it was related to the movement of the solar system through certain parts of space. Yeah.
In one of your graphs, you had South America as an extreme extinction, big degree. Why is that in South America?
I can't tell you specifically. Presumably it's the vulnerability of, well, not just the Amazon, actually. The Amazon is vulnerable, as we know, but also places like the Pantanal in Argentina, which are amazing sort of wetland, huge area of wetland ecosystem, and again, just vulnerable to agricultural practices and so on. And again, there's reserves in that, but I think it's because it's got lots and lots of, South America has a huge diversity of species, and therefore, you know, it's got a lot to lose as well. Yeah. Yeah.
Could you talk some more about moa extinction? Because I've always heard it was humans and the time frames involved.
Yeah, so I can't remember the details of that. I mean, I think basically within 200 years, most moa were extinct. And it was simply, moa had evolved on New Zealand. New Zealand was quite a small place, and their breeding rates were very, very slow, very low, just keeping them at replacement level. They could probably withstand very low levels of predation. And I think it was just, you know, and there's other species around the world like this, but you only need to take just a tiny bit of their offspring, and you put them on a downward spiral. The moa are a fantastic example, are a very clear example of how easily that actually can happen in certain circumstances. If you'd had a continent the size of North America and the moa was spread over that whole continent, it would have been a much harder thing to do. But because it was actually quite a small area, there was nowhere really, you know, to escape that predation pressure. It was enough to drive them to extinction. Yeah.
I was surprised to hear that the definition of megafauna is anything over 45 kilograms. Most of us here are well over 45 kilograms.
Yeah, well that's right, yeah.
Why was that figure chosen?
I can't remember the details. There was a reason for that figure of 45 kilos. I can't remember what that is. Oh, and what I should have said about the megafauna, the one continent on the planet where it didn't happen at all, of course, was Africa, which still has nearly all its megafauna. And again, not well understood. I think the explanation is, the thinking is, because Africa, humans and the megafauna sort of evolved together over 2 million years, and that they'd sort of come to an equilibrium, and it was just elsewhere. So Africa was the only place that escaped that megafaunal extinction.
Can I just ask one thing, James? Do you think that First Nations people knew about mass extinction, and we kind of haven't explored that?
I don't know one way or the other. I'm certainly. It's interesting. There's a sort of project that hasn't kicked off and it hasn't been funded, but one of them was to look at the Maori understanding of extinction, because depending on who you talk to in the Maori communities, some communities had no word for extinction. It wasn't in the vocabulary, but others did apparently. So that's Maori. Look, I don't know.
I just thought of the Aboriginal people
Yeah.
and their cave joins, and I just wondered if anybody had ever looked
What
at
their
First Nations people.
their stories
like
are.
hear about this.
Yeah.
Yeah, they had evidence from the mythology.
I mean, they would have seen the extinction of the diprotodon. The diprotodon would have been a fantastic food source for them. I mean, one diprotodon would have kept a tribe going for a long time. I don't know if there's an oral history of that. It's a really interesting question. I don't know. Yeah.
Why is New Zealand so close to where it's, as you said about South America was in red, and we were, sort of pretty, we're pretty close to that,
Yeah.
that we were not white.
Well, we've already lost a lot of bird species. I mean, a huge number of bird species. Because we've got a lot of species that are that are at high risk at the moment. I mean, think of all the kakapo and the kokako and the saddleback, and list can go on and on and on. There's lots of things. Because we've got a lot of species that have small population sizes, very small population sizes, and when you've got a small population size, you only need a new disease to come in or something to affect some environmental catastrophe in one area to affect your population. That makes us vulnerable. In the marine realm, it's because our marine species the ones that live around the coast have nowhere to go. If you're in tropical America and it gets hot, you can move up the coast or you can move down the coast and just keep going, huge thousands of kilometers until you find somewhere that the species over successive generations. In New Zealand, we don't have that luxury. We have nothing south of us. So our marine fauna is sort of captive. They're stuck.
We're so small.
Yeah, because we're so small, yeah. And we've got this amazingly unique endemic fauna though, because we've been isolated for so long. So we've got a lot of endemic species and they don't have a lot of space to live in.
Further questions?
Just
sheer curiosity, what are the settings between the lava flows and the deep canal?
Well, in a few cases, it would be you'd just start to get soil development, you know, a lava flow, and if there was a few hundred years in that particular place where there was no more lava, you'd start to get a bit of soil developing, perhaps, and a few plants growing, and a bit of wind-blown dust, but mainly just for volcanic debris, ash, you know, ash and a bit of soil development, then you get the next lava flow coming on top. But a lot of those lava flows would have happened so quick, you know, a few years apart or decade apart, they wouldn't even have had time for that to happen.
I'm interested in mollusca and shell world, and I'm concerned that we're getting smaller shells in New Zealand and less of them. And is there anybody doing any research on what's happening to our mollusks?
Well, that's my particular interest, and I can say that one of the things we've looked at is whether large species are more resistant or small species, and sure, large species are more vulnerable. Yeah, I'll put in a big grant to do more of this work. Actually, and I didn't get funded, so so not specifically particularly happening right now, but I've got a sort of project ticking along in the background with a former student. We're trying to address some of these questions, but we can't. That's exactly the sort of thing we can look at. How does body size? We know from the fossil record, body size is one of the absolutely key factors in extinction risk. So yeah. So it's not really happening. It should be. I'd like it to be happening.
I mean,
I'd like to be doing it.
So many of the estuaries have got millions of dead cockles that are immature.
That's really interesting to hear you say that. Actually,
I've seen it again and again.
Yeah.
I've seen it further north. I've seen it out here in Wainui. I can name numerous places where there are dead cockles. They're immature, and they're just millions of them.
That's really interesting. I don't know if anyone at Cawthron or at NIWA are working on that.
I would like to know whether somebody's keeping an eye
specifically on that. That's interesting. I might follow up on that. That's really interesting. Yeah.
This is just a guess, but after those ravaging floods we had in 2010, 2011, and that last one was on the Wainui side of the bay, there was a huge silt slide down into the ocean, and that ruined a lot, I think, but
smothered the fossils.
Would have gone on for, I'm not sure.
Yeah, I mean that could easily smother the animals. Yeah, that could easily be an explanation. Yeah.
Well, I'm sure many have got further questions they'd like to ask, and if James is still around, perhaps you might go up to him individually. Well, it's not been much chop outside, but we more adventurous types who have come out tonight have been treated to a fascinating and quite challenging talk. I suspect that probably not too many of us have thought about the role and significance of extinctions in maintaining biological evolution. It's good to be confronted with that again. And I think all of us are acutely aware of the challenges that we face in preserving our own biodiversity, which is quite amazing in this country. Interesting to hear you say, and I think we like to pat ourselves on the back and think we are innovative, but I hope that doesn't make us too smug about,
that's
about maintaining this precious biodiversity. And in fact, just now while you were talking, it's not just the animals that are threatened. This area has an amazing biodiversity and plant life as well, and in fact there are at least 4 species of plant that are found on Mount Bowness only, and they're endemic to New Zealand, which means they're found nowhere else in the world. So we've got some challenges ahead to do all we can to maintain this.
My students were feasting themselves today on banana passion fruit, which is a terrible noxious weed, but they were, I mean that smothers plants, and I know, there's problems with things like that.
Anyway, thank you so much for coming out tonight when you've got a very busy schedule, I know, and we appreciate it greatly.
You're very welcome. Thank you.